Okay, we have Sumilan, and he is going to talk about information scrambling and butterfly velocity in p-spin glasses. Okay, 30 minutes, I will raise my hand, and you have 5 minutes.
Oh, this was your seat.
Okay, can you hear me at the back? No? Can shout. Hello? No? Hello? Can you hear me now? Okay, thanks. Okay, so let me begin by thanking the organizers, Rituparno, Shantan, Ranjini, and Srikant, to giving me opportunity to talk here. So I actually don't work on glasses, but the some thing that we did on glasses for some interest that I will try to tell you. Hopefully in the interdisciplinary spirit, it will be not too boring for you. So I'll be talking about this thing about information scrambling and what it. But before that, let me just acknowledge the people. So this work actually done few years earlier. We have done some recent work, more recent work last year, but I'm mostly going to focus on this older work because this might be more relevant to the people here. Because it relates to the p-spin glass, but if you are interested, there are other kind of spin glasses like this Sajde VA spin glass model you can find in these works. Okay, so let me just begin by telling this concept of information scrambling. So of course this concept of classical and quantum chaos, I mean very old, particularly the classical chaos, and is this same standard picture. For classical, let's say for a single particle chaos, that you have a single particle, there are trajectories starting from initial conditions which differ by a small amount. And then if the system is chaotic, then these trajectories will go away from each other in an exponential fashion with a rate as we determine by this Lyapunov exponent, let's say in this case some maximum Lyapunov exponent. And then you can find a Lyapunov regime which you can kind of tune by this quantity epsilon, the initial difference of these two trajectories. And so basically this kind of growth you will see over a regime which is from lambda L inverse to lambda L inverse log 1 by epsilon, typically when this quantity become order 1. Okay, so this is about classical chaos. Now how do you go to the quantum chaos? And this was done again by Larkin and Ovchinnikov. In a very work which is kind of unrelated to this, but they sort of found this in a work on superconductivity. So the idea is that if you have a system which is close to the classical limit, like a semi-classical system, so then what you can do, you can this quantity that you have over here, this initial condition sensitivity, you can write as a Poisson bracket, and then you can transfer the Poisson bracket to a commutator. Of course, you have to divide by h bar because otherwise the dimension will not be correct. And the another problem is when you write a commutator, this of course no longer a number, you cannot find a number for this. So you have to do some expectation value with respect to some state. Now it turns out that if you just take an expectation value, that will be just typically standard 2-point correlator, and those cannot really grow. Because these evolutions will cancel each other. The standard 2-point correlations don't grow, we know. So what you do is the next obvious thing, you square it and average, okay, and you take some state. And it turns out that if you are some semi-classical limit, meaning in some sense this h bar, which is like this epsilon, which you could control here. So this h bar essentially defines a Lyapunov regime if you are close to some semi-classical limit. Okay, and in those systems you can have a Lyapunov exponent which is obtained from a quantum commutator square average and defines a Lyapunov exponent, a quantum Lyapunov exponent, right? Okay, so what is the idea of scrambling to do with this, and what is meant by scrambling here? So idea again is related to this. So let's say now what you do, you take any quantum system and you just look at two operators, let's say two local operators. And you look at this quantity, and if the system is quantum chaotic in this sense, then you will have a Lyapunov exponent. And why does it grow in those cases? So the idea is related to very simple thing about quantum mechanics. that is this operator growth. So if you have an initial operator which is local, let's say some spin operator, you are saving some qubit with some quantum information, and then as the time goes, this no longer the same operator, okay? So the operator changes, so it becomes more and more non-local, which is coming from these nested commutators. And so the operator changes its structure, so any information you keep initially in a local space, it becomes global, and this is how you have to save quantum information, so you have to care about such things, okay? So that's what is giving you this growth, okay, in this quantum chaotic system. And you often look at quantities which is sort of related to this commutator square, which is essentially you expand that commutator square, you will find there is a quantity over here which looks like this, which is called an out of time order correlator. The reason being it is not like standard correlator in quantum mechanics. You see that there is a staggered ordering of time, that is that you first have 0, then t, some positive time, again 0 and t. So that's why it's called out of time order, okay? And you can also obtain, yes?
What do you mean by growing in size?
Yeah, so you can take a simple example. Let's say you can take a spin operator, and if you take some Hamiltonian, let's say some transverse field Ising model or something, and if you just do this, you will see that this operator, the first term will be a spin operator, then the second term will involve two operators in nearest neighbor side, and then next nearest neighbor side. So the operator which is initially the operator is no longer the same at a later time, the Heisenberg operator, okay? So that's the idea. Okay, so you can also look at some spatial information, spatial propagation. Now you can take, if you have a spatially extended system, you can take two operators, let's say one here at x equal to 0 and another at some other position. And then you can again look at this commutator square. So now what will happen is that there will be some time this information that this operator will grow and will eventually overlap with this operator, which is somewhat distance away, and this information will propagate. Okay, and it turns out that it propagates like a relativistic light cone with some characteristic velocity, which is called the butterfly velocity. So basically this chaos, you can extract these two quantities, the lambda L and the butterfly velocity. So it tells you how chaotic this system are, how fast the information which you create locally propagates and become global, okay? So that's the idea of the, so this is what is called information scrambling. So essentially you have some local information which becomes scrambled, like a scrambling of an egg, and it becomes completely global, okay? And then you cannot easily recover this, and this is something that of course if you are manipulating quantum information you have to face, okay? So that's why you want to understand this. So now the thing is that why care about this apart from this? So that turns out that this quantity, that this out of time order correlation, correlator has a very universal property. So it turns out that if you take any quantum thermal system, the system in a thermal ensemble, then what you can show that this lambda L, which is this Lyapunov exponent, for any quantum system in nature in a thermal ensemble is always bounded by 2 pi kBT by h bar. And it doesn't depend on any coupling constant of the system, it just depends on the temperature and fundamental constants of nature, right? So this is like a very amusing thing which was found by these people. So this is called Maldacena, Schenker, Stanford bound, and it turns out there is a model which is to interest to maybe quantum condensed matter, but also spin glasses, because this model actually originated from a spin glass model, which is the Sachdev-Ye model, which is now called Sachdev-Ye Kitaev model in this modified modern version. So let me just describe very briefly this model. So this model, so people who have worked on p-spin glasses is very similar to p-spin glass model. Only thing is it defined in terms of fermions, and these fermions, so basically you have some 4 fermion interactions which are on sites, n sites. And this is an infinite range model. All sites are coupled to every other site with a 4 fermion coupling which is random, okay? So just like a random model, like a spin glass infinite range model, although this doesn't have any spin glass state, it has some kind of a spin liquid type state or some kind of a non-Fermi liquid state. But the most interesting thing about this model is that this model exactly saturates this bound, okay? This Maldacena, Schenker, Stanford bound. And this model is not just a figment of imagination. So people actually have proposed realization of this model in graphene flake, and people have claimed to have realized this in some of the features, even in this graphene flake, okay? So So this is the thing. So now the thing is, so this is about, so this is a zero-dimensional model. Here you can only define Lyapunov exponent, lambda L. So if you want to get some information about spatial propagation, like butterfly velocity, then it turns out what you can do, you can imagine these zero-dimensional models like a quantum dot, right? And then you can put them in some lattice that you like, okay? So basically you create a space. And in that case, you couple this quantum dot in some way, and you can calculate different things like transport and other things in this type of systems. And in this, if you construct such system, it turns out that there is also some kind of a universal relation. That is, in this type of model, you will have a lambda L, you will have a butterfly velocity, but these models will also have some transport, typically diffusive transport. Now, this diffusion and that chaos quantities are completely unrelated, but it turns out that in this model, there is a relation, I mean, some of this model you can find exact equality between diffusion coefficient and this chaos diagnostics, okay? And of course, dimensionally you expect some relation like this, but these relations turns out to be exact in some of this model. So this tells you that there could be a relation between transport and chaos, okay, in some of the models at least. And if you have such relation, then it leads us to this question in condensed matter that are there bounds on scattering time, okay, fundamental bound, okay. So that's why people are interested in this. And then because these are sort of universal thing, you can ask a lot of questions that whether you can characterize phases and phase transition in terms of this quantity, okay, Lyapunov exponent and butterfly velocity, and what its consequences are. So this program, yes, yes.
So does this model have semi-classical limit?
Yeah, it has a semi-classical limit of a different time. It's a large n limit. It's, so this epsilon parameter that I show is like 1 over n in this model.
So for fermion spinless?
Yeah, it doesn't have a straightforward semi-classical limit, but you can write some dynamical equations which has this type of, it turns out that there is a control parameter which is like semi-classical, but you cannot, so I'll discuss this in more detail. Okay, so this program has been taken forward, so people have tried to characterize various type of systems, just a list here, using this type of chaos diagnostic and trying to connect them with transport. So I'll of course not go into it. Now let me come to this question that why study chaos in glasses, okay? And as we all know that there is a natural reason, and this probably have been studied also in some other context, but I mean I don't need to discuss this. So you have this complex relaxation in glasses, but the most sort of important motivation you can take is this rugged energy landscape. Now, in certain temperature range, you essentially sample this rugged landscape. For example, its saddles and minima, right? Now, these saddles are unstable directions, so you might think that there might be a regime where, because you have a lot of saddles, so if you start a trajectory, then this trajectory will be very sensitive to initial conditions, right? So when you are dominated by saddles, then these trajectories may be dominated by these saddle points, and you might have a larger Lyapunov exponent in those regions, and it might be able to detect some physics of glasses also. But it is also interesting from the point of view of information scrambling, okay, because you will have a very large Lyapunov exponent or chaos in that regime. So that is sort of the basic initial motivation. That is, it may lead to sensitivity to initial condition. There are other motivations that this type of glassy models has some solvable, very well-studied large N models, and they have other aspects which is not there in SOIK model. For example, symmetry breaking, replica symmetry breaking, and other things. So how do they play with chaos? Okay, and then you can ask what happens across. So this is like an inverse time scale. So what happens to this time scale across glass transition? Does it diverge? Okay. So you can ask those type of questions, and you can also ask some other questions like what happens. So as a theorist, let's say if you can tune, as you see some of these glasses, you can tune h bar, and you can ask that by the bound, this lambda L is bounded by 2 pi kVt by h bar. So if I just take the bound and plot it, so then as I go to classical limit, this bound diverges, which means the classical system doesn't have any bound, okay, by this argument. But an actual system, when you have a well-defined classical limit, typically you will have some classical chaos, right? So question is, what happens when you tune this? Does it sort of smoothly goes to some value? Is the classical system always more chaotic than a quantum system, or can it be that quantum system become more chaotic than the classical system? So some of this question actually you can will see that we can address in this glass models. Okay, so with that, so the model that I'm going to take is a very well studied model, but I'm going to take a quantum version of this model, which is the quantum p-spin glass. And if I don't get time to go over all the results, so I'll just discuss the result here, tell you the result that we get here. So this is the quantum p-spin glass model. I'll discuss the model in the next slide. But basically what I'm going to discuss is a chaos phase diagram of the model. So this model has essentially two tuning parameters. One is temperature and another is h bar, which is some quantum fluctuations. And what I have plotted here is a phase diagram of chaos. So this color is basically Lyapunov exponent, okay, which I have plotted here. So before going into the color, so the well-known phase diagram of this model is that you have basically at h bar 0, which is your classical p-spin glass, you have a transition from a Margillan spin glass to a paramagnet, which is here. And as you increase the h bar, this temperature decreases and eventually goes to a point, basically a tricritical point, and then after that there is a first order transition. Okay, so this is the model as a function of h bar and t. So now what I am plotting here is if you track this chaos, so this chaos is largest, you see somewhat above this transition, okay, somewhat above this dynamical transition, it is largest. And this temperature, temperature at which chaos is maximum, you see that it tracks the dynamical transition temperature, but it is not at the dynamical transition temperature. It is somewhat above. Okay. So, and another thing is that if you take the h bar going to 0 limit, this is the p-spin glass model. So above the dynamical transition, it is describes the dynamics of classical supercooled liquids, right? So you can get idea about the classical supercooled liquid, the chaos in classical supercooled liquid by this. And it turns out that after this work, so people studied this, and what they found that where the chaos become maxima is actually related to the maximum complexity of the landscape. Okay, in some sense, so basically you can do these calculations of the number of saddle points and number of stationary points, and you find that this point, which is E equal to 0, exactly corresponds for the classical limit over here where the chaos has a maxima. So you get maximum chaos, you get maximal complexity. Okay, so this initial intuition seems to be working here, and the next question is that how do you study this? Okay, so this model is 0-dimensional. So I'll discuss also butterfly velocity, and the idea is that you can make a chain of these quantum dots of p-spin glass, and you can essentially make a model where again you can study the butterfly velocity. Okay, so that's what I'll discuss. So I'll show you that there is some butterfly cone in this system. Okay, so let me discuss the model. So this is the standard p-spin glass model. So if you have just the last term, then this is the standard p-spin glass where you have p-spin interaction, some random interaction like the SYK model. You put a spherical constraint to make the model non-trivial. Here, and there are a lot of beautiful work on this for many people. I am only mentioning few literature here. And here what we are going to do, we are going to induce a dynamics, a quantum dynamics by putting a momentum. So basically treating this S as a position coordinate and then defining a canonically conjugate momenta, define a quantum dynamics. Okay, so that's how you induce the dynamics in this system. And this model has been studied by Letitia and others in several works. Now, the good thing about this model is that you can actually tune h bar in this model continuously. Okay, unlike the SYK model, which Dibyendu was asking. So in this model, you actually have a semi-classical limit. Okay, so you can actually tune and go to h bar 0. These are not fermionic model, so you can take this limit. And as I already discussed the phase diagram. So if you go to, and then what I'll do, I'll take h bar going to 0 limit also, and that gives you the mode coupling dynamics over here, and it captures the chaos also. Okay. Okay, so I'll go over this bit quickly. So these are technical part, but very standard things in people working on p-spin glasses. So the way you solve this model is a dynamical mean field theory, which Giulio Viroli was mentioning. but in this quantum case, so essentially there are some equations. So there are some basically order parameter, which is like a spin glass order parameter, which is defined in terms of some correlator of the spins, and you write down some mode coupling like equations with some self energies, which is exactly obtained in this model. And what you tune is this dimensionless order parameter, dimensionless quantum parameter, which is like h bar. Okay. So this model again has two kind of phases it can have. So if you have this order parameter, you have introduced replicas, and if you have replica diagonal, then you have a paramagnetic state. And you can also have this one-step replica symmetry breaking, which is exact in this model, which is again some kind of one-step replica symmetry breaking on such with the Edward-Anderson order parameter. So you can do all the standard thing in this model, which are all done by Letitia and others long ago. So all those things you can do. Okay, and but the main important thing is you want to calculate the chaos here. So that's the additional bit. So how do you calculate this OTOC? So that turns out, so this turns out you have to do a real-time dynamics, and you have to calculate a quantity like this. As I mentioned earlier, it has this staggered ordering. There are some regularization you have to do for some technical reasons, so let me not go into that. But basically, this is the quantity you want to calculate, okay? And it turns out to this quantity looks something like that, and it turns out to calculate this. Again, some technical thing, you need like what is called the Keldysh formalism, and it's different from standard Keldysh formalism because you need basically 4 branches to basically write this kind of staggered ordering, and you can naturally write this on this contour order. So there are some technical thing about this, but you can do all those things. Now, one thing is that we also want to calculate chaos in the marginal spin glass. So typically, if you are in the paramagnetic phase, then you can just do the disorder averaging on the Keldysh Keldysh partition function, and you can obtain this. But if you want to get the marginal spin glass, that's not enough. So what you have to do, you have to also introduce replicas, okay, even in Keldysh, and you have to do this. These are again known from some earlier works. So this is what you have to do to calculate this object here across the paramagnet and the marginal spin glass. So basically, you have to do Keldysh, and you have to still use replicas, okay, to impose this. And what you do, you calculate this object, and there is a part of this object. So in this model, this is like exactly calculable as a 1 over n expansion, and there is a quantity which you can obtain, which I will show in the next slide, which basically, if you have a chaos, goes like e to the power lambda LT. Okay. So these are calculated using some ladder diagrams. So main thing is what you ultimately find, this quantity which is supposed to grow like e to the power lambda LT, you can write a kernel equations for that. Okay, and the kernel, the main ingredient of the kernel is it's obtained from these saddle point solutions that Letitia and others found out. Okay, so that is the input to that kernel. So it has different kinds of retarded and some kind of correlator, which are called Whitman correlators, which appears here. But all of this you can calculate from the saddle point solutions, okay, which are known. So that's the main thing. Now you can ask that how does the spin glass order parameter appears in this equation? So it turns out it does appear. So this object, which is the Whitman correlator, the main difference of this object between the paramagnet and spin glass is that this there is a Edward-Anderson order parameter that appears. When it is non-zero, it appears in this kernel, okay, and that distinguishes between the paramagnet and the spin glass. Okay, so all this information goes in here, and then you can kind of solve this kernel self-consistently and find lambda L. Okay, so and then obtain this. So I'll show you the results. So this result I have already shown you, this colored thing. So and let me just go over it bit slowly. So this is the region, let's focus on this region. So and let's look at as a function of h bar. So I am basically going like this, okay, going like this. And what I find that when I am at high temperature, so when I am at some high temperature, yes.
So as you said, h1 tends to 0, you have classical
Yeah.
limit, so that model has a classical limit, and you can study directly the
Yes.
dynamics there.
Yes.
So that also.
That we have not done, but you can directly write down the classical equations, which is again known from classical p-spin glass dynamics equations. Okay, so people have studied those
So
equations.
there you can directly
You
calculate
can
the Lyapunov
directly calculate. We didn't do it here. Okay. Okay, so if you are at very high temperature, then you find that as a function of h bar, what you expect that you have a quantum system which is less chaotic and it become more chaotic as you go to the classical limit, right? But as you come close to this temperature, near this dynamical transition temperature, what you find as you vary h bar, you have a quantum system which is less chaotic, it become more and more chaotic as you go to the classical limit, but eventually it goes down again. So that means the quantum system can become more chaotic than a classical system, okay? And that happens in this region where you have this maximum complexity, okay? So this is what you find in this. You can also study as a function of temperature. There is again is a peak, and so this is sort of the main point here, that this relaxation, something is happening here which is giving you this kind of non-trivial features to the chaos. So let's try to see. How much time do I have? Okay, 7 minutes, good. So I just quickly go over. So you can also look at the spin glass phase, and you can ask that what happens to the spin glass phase, the chaos in the spin glass phase. And what you find that the spin glass phase is actually always, as you increase h bar, the chaos increases, okay? So here actually, as you make the system more and more quantum, the chaos increases, and you can actually understand this. So basically this can be understood analytically. I'll again skip the details. So you can solve these equations analytically. Yeah, yes.
Questions, I'm confused. When you mean the spin glass phase, when you mean the spin glass phase, you do not refer to the static transition.
No,
to the thermodynamic. You only consider the dynamical transition.
Dynamical transition.
And to zero temperature, this is what you call the spin glass phase.
Yes, yes, yeah. So only the marginal spin glass we generate it by putting the replicas. Okay, otherwise you have to do the edging and then take the waiting time to infinity, like those standard procedures. Okay, so it turns out in the spin glass phase you can solve this exactly these equations under some assumptions. The main point why the chaos increases as you increase the quantum fluctuation, it turns out that this Lyapunov exponent is inversely related to the Edward-Anderson order parameter, okay? And when you increase, basically when you increase h bar, the Edward-Anderson order parameter goes down, and that's why the lambda L increases, okay? It's basically destruction of the order by quantum fluctuations that increases this Lyapunov exponent in the spin glass phase. Okay, now let me try to connect it to the glasses. So what is the sort of is there any relation with the complex relaxation? Okay, so what I have plotted here is I have plotted for the classical limit. So basically almost h bar going to zero limit, and what I have plotted as a function of temperature, the standard plots in glasses, which is the correlation function, like a spin-spin correlation function in this case. And I have plotted as a different temperature. So as you go to lower and lower temperature, you start seeing this complex relaxation, basically the beta and alpha plateau, okay, that appears below certain temperature. And you can basically try to obtain from here the alpha relaxation time, and the alpha relaxation time of course diverges as you approach this dynamical transition. And I have plotted on the same plot lambda L inverse, which I have shown earlier, which had a peak above the dynamical transition. So lambda L inverse has a minima above the dynamical transition. Okay, so the one answer is that lambda L inverse doesn't diverge at the transition. Okay, so it's not related to this diverging time scale. This is not very surprising actually, but I'll not go into that. So this is one thing. The second thing is that you can try to track the onset temperature, that is when this two-step relaxation sets in. And if you find the onset temperature numerically, and what you find that the onset temperature exactly, so I have plotted here by T beta, okay, exactly coincides with the maxima of the chaos. Okay, so it seems whenever you have this complex relaxation, so there the maxima is appearing, right? So we have some understanding of this. In fact, we can solve this relaxation for Debye relaxation, this kernel equation exactly, and we can show why it has this maxima and what determines this maxima. So this can be done in this system, but let me just sort of end. So I'll just one or two slides I'll end. So as I said earlier, that these people after this work, so they actually tried to find out the relation between this maxima and the complexity. So what they did is they did the calculation, I think quite standard calculations of this complexity, which is the number of stationary points and also the index of the stationary point. Okay, and so they did this calculation in kind of a micro-canonical way, basically as a function of energy, unlike here, which is as a function of temperature. But you can connect this energy to temperature as they do, and what you find is that this temperature E equal to 0 exactly correspond to T equal to 1 in this thing. And there you have this maxima of this complexity, and also you have mostly half unstable and half stable saddles. Okay, and that's why this chaos is maximum. Okay, so this so okay, so I'll basically end. So as I said that you can make this sort of extended system over here, and you can do it in a way so that this phase diagram doesn't change, and you can calculate again. There are set of diagrams and all slightly more complicated, but basically you can calculate this this butterfly velocity, and what you find, the butterfly velocity also has same phase diagram. Okay, it also again has a peak above the dynamical transitions. So information not only grows fast but also moves fast somehow when you have this complex relaxation setting in. Okay, so that's basically this. So with that, let me just stop here by saying that again the same thing, that this information scrambling and information propagation seems to be coinciding with the onset of glassy relaxation and the maximum of complexity. Okay.
Okay. Let's thank Sumilan for this engaging talk, and yes, Jill. And then Patrick.
So, if I understand, so you're saying that the maximum of chaos is when you have the maximum basically of saddle points.
Yes.
But that when the saddle points, there are no more saddle points and they vanish, then it has no relation to chaos. This is strange.
Yeah, so it's just because it is at some temperature I'm measuring, right? So it's sampling, not sampling those saddle points any longer, right? So it's sort of going towards the minima, basically, right? So it's the sampling of that saddle point. So the sampling of the saddle point is optimal around that temperature range.
At TMCT, where this K goes to 0 or goes to 1.
Right.
Okay, one over that.
Right.
So there
it is there. I mean, the chaos is still there, right? So chaos is never. So by the way, chaos is never going to 0 anywhere. Even in the spin glass phase, there is a chaos, right? So it's just the thing is the propensity is maximum when you have just the onset of this maximum unstable direction, equal unstable and stable direction, right? So chaos is always there. It's not going to 0 anywhere.
Okay, Patrick. Then Julio.
Yes, sorry for the naive question, but what onset temperature are you using here?
Sorry?
What do you use as the onset temperature? What is the definition?
Definition of onset temperature here.
Onset temperature, yeah. Okay. Yeah. So this here this definition may not be the standard one. So the way I used it over here. So essentially, we try to track down when you have beta and alpha relaxation. Okay. So at what? So up to some temperature, it has two steps. So basically, it's the onset of two-step relaxation.
Okay, thank you.
Yeah.
Okay. Julio.
What is the intuition of why lambda, so the lambda L should be maximum at the onset of glassy relaxation? Because in principle, I would have thought that Lyapunov exponent has nothing to do with glassy relaxation in the sense that it's short time.
Again, so it's a very good question. So I think there is no universal relation. Okay. So this model, somehow it turns out that there is a peak and it could be some parameter issue. Okay, so we actually have studied another model, this has the VA model, right? And there it doesn't happen. Okay, so I don't think there is any universal relation between these, because you are right. So the chaos is somewhat much more shorter or intermediate time property, right? Which might not have anything to do with.
Sachdev model doesn't have a glassy phase.
No, so that is so such the VA model which has a glassy phase, and there has a phase diagram, but you are right. So this is not I don't think it's a universal aspect, right? For some reason it is happening here. As such, the chaos should not have any relation, I would say, to this, but somehow here it is tracking for some reason, maybe some coincidence of the parameter is tracking the two-step relaxation.
Thank you.
Okay, so if there is no more. So there is one last question here.
Yeah?
Yeah.
No, this is just the lambda L becoming, it's a color coding, the lambda L becoming smaller. There is no.
Okay, so we'll take the last question and then.
Hello. I'm not much aware about the quantum system, so I have just one question. How does bounds on the lambda L relates to the Lieb-Robinson bound?
Yeah, so
Is there any implicit relation there?
Lieb-Robinson bound is sort of there, right? I mean, so in general, there is no relation as such. I mean, they are both related to the operator growth, but they are sort of different measures. So one is operator norm measure, and this is, so Lieb-Robinson bound is a state-independent statement about the growth.
Yeah.
Okay, but this one depends on the state, that is the temperature.
Okay.
Right? Yeah.
Okay, so let's thank Sumilan for this nice talk. And so we go for lunch and we come back at 2, and we have session on AI, and the talk will be by Anup and Ludovic. So there is a change in the schedule. So please have a look at the schedule. And then we have an overview talk by Jill at 3:10. It is updated now. So the schedule is updated. So in the post lunch we have 3 talks, and then we go into poster session.